So we've already talked about Newton's laws of motion, and Newton's laws of motion brought in the idea of forces. And so here today we're going to look at forces and some more specific things about them. Starting out, an object is said to have a net force acting on it when there's any unbalanced force acting on it. But it can also have a zero net force, and a zero net force comes from forces that cancel each other out. And so a net force is really just the vector sum of all the forces. I remember vectors have directions, so really we end up carrying only about two directions, the up and down and the left and right, or the x and the y. And then those forces, we can figure out the net force. Even if the force is being pulled at an angle, just like we did with projectile motion, we'll break it up into a vertical and horizontal component, and we'll come up with a net force that way. A couple special types of forces. One is what's called the normal force, also sometimes called the support force, and it is the support force that is perpendicular to the surface. And so when the surface is horizontal, that's always equal to the object's weight unless the object is accelerating. So for example, if you have your books sitting on a table right now, the support force of the table is equal to the weight of the books. Having said that, if we were to slope the table so that the books were sitting on a ramp, the support force is always perpendicular, and so then because of that, the normal force out this way ends up being different, because the vertical component still has to be able to cancel out with the weight of the books, the gravity. But normal forces are always perpendicular to the surface. Tension is just another name for a special type of force that occurs in a rope or any kind of thing that we use to suspend something or pull on something with. And tension forces are always directed away from the object, and again, they are related to the weight of the object itself. Of course, weight is nothing more than the force due to gravity acting on the object. And I mentioned this already, but even though we know that F equals ma, we also have a lot of other formulas we'll come across for force. And so then anytime we see force in a formula, well, you should think we could substitute that force with the ma of Newton's laws here. We won't deal with friction from a calculation standpoint very often. Most of the time in physics we ignore friction. I often joke that physics is a study of the ideal or the perfect world, and that if we could if we have to deal with that stuff, we'd let the engineers do it. And that's not totally true, but most of the time here in high school physics, we will ignore frictional forces or only talk about them theoretically. Okay, what would happen if we brought in friction? But sometimes we cannot ignore them, and so we do need to talk about them a little bit. And there are two basic types of friction. There's static friction, which is the frictional force that acts on an object when there's no motion between the surfaces. It's basically what holds the object at rest and keeps it from sliding around. You'll have objects slide around if the table's not perfectly level. You'll have this happen, I don't know, with any kind of slight breeze. You end up with the object drifting around. And if it doesn't do that, it's because there's static friction. And it's not totally accurate to say this, but you can imagine it basically that the two surfaces are rough and they kind of lock together. And so then you can't get them to move past one another. That is static friction. It's what keeps the object at rest, and you have to overcome that static friction if you want to get it going in the first place. Kinetic friction, just like kinetic energy, is friction of motion. It's a frictional force that acts as a object slides or moves over or through another object. And we actually need kinetic friction for an object to move. And that may sound silly because friction, of course, works against motion, but you have to have friction to be able to move anywhere as well. If it wasn't for friction, if we truly lived on friction-free surfaces, then your car tires, for example, would just sit and spin. And you can notice this in winter. If you ever end up on a big ice sheet, your car tires can't grab the ground, and because they can't grab the ground, there's no friction between them and the ground, they just sit there and spin, and you don't go anywhere. You have to have some friction to be able to go, even though friction makes the calculations a little bit uglier and we tend to ignore it. Also, air resistance is related to friction. Really, it's just it's kinetic friction, but it's a special case because we're talking about moving an object through air, and since we do refer to air resistance often enough, I've listed it as a separate point here. And terminal velocity is when the air resistance, or the force of friction, is equal to the object's weight. This is what happens when you have an object that's falling, and it ends up there's a limit as to how fast you can fall. Even though gravity wants to keep accelerating you, which would speed you up and speed you up and speed you up and speed you up, there comes a point where the air resistance begins to slow you down, and you don't speed up anymore. You're still going stinking fast. If you don't have a parachute, you're still probably going to go splat when you hit the ground. Terminal velocity allows you to begin to slow down, and eventually you get to a point where you're moving at a constant speed but no longer accelerating. And of course, parachutes are a great example of this. Parachutes give you a really high air resistance, really high force of friction, and so then you end up with a much lower terminal velocity, a maximum speed that you can reach. Having said that, terminal velocity is a little difficult to calculate because the more oddly shaped an object is, like a person, the harder it is to calculate. A lot of times in physics, we like to deal with nice, neat geometric shaped spheres and cubes and such. Having said that, I believe the anecdotal rule of thumb is that terminal velocity for a human is around 100 miles an hour. Anyway, don't copy down this slide. I'll hand this one out to you in class. It's not super important to list these. It's just something that you should know. One interesting fact about frictional forces is that they appear to be independent of the areas of contact. It doesn't matter whether we have an object up and down or on its side. Here, there's more area, but the frictional force seems to be independent of that. They both appear to be proportional to the normal force, that is, static and kinetic friction are proportional to the normal force or to the support force. Of course, the normal force is usually related to the weight, but it's not directly the weight if the surface is sloped. And so that's why we say that frictional forces are proportional to the normal and not proportional to the weight of the object. Sliding friction or kinetic friction appears to be independent of speed. It does not matter how fast you're going. Once you get going, the frictional force doesn't seem to change. This is not true for fluids. Fluids, as we'll see later on in the year with Bernoulli's principle. Yes, with Bernoulli's principle, that friction decreases as you increase the speed. And fluids, of course, would be liquids or gases. And then there is a formula that we can use to calculate friction. Do be sure that you take this formula once you get this slide printed out and transfer it over to your formula page. But the force of friction is equal to the coefficient of friction multiplied by the normal force. Now, force of friction I have abbreviated here, FRIC. Sometimes it is just F sub F. The coefficient of friction, that letter is the Greek letter mu, which is their letter M, but looks like a U with a tail on both sides. But that's the coefficient of friction. Usually what will happen is you will be calculating the coefficient of friction, or you'll be given the coefficient of friction and asked to calculate the frictional force. And for every material, the coefficient of friction is different. It's a constant, but it's a constant for a particular material. And so it's true for that material, but not true for others. And so most of the times when we use this formula, we're actually using it to solve for the coefficient of friction. Equilibrium is if there are no net forces acting on an object, then the object will not accelerate. That does not mean it is stationary. An object can be moving and be in equilibrium if it is not speeding up, if it is not slowing down, and if it is not changing direction. Then there is no acceleration, but it can still have a velocity and move along in equilibrium, where the support force of the ground cancels out perfectly with the weight due to gravity, and the object just moves along. Object in motion wants to stay in motion, but that is equilibrium. And I just read an article the other day that talked about how sometimes when we talk about action-reaction, we think it deals only with moving objects. But if I squeeze on this thing here, we could say the action is me squeezing, and the reaction is it pushing back on my hand, even though nothing's really going on there. That is a system in equilibrium, and that has an action-reaction pair. Equilibrium is just when there is no net force acting on an object. And so, simply speaking, equilibrium is the net force is equal to 0, and the scary math terms that you see here, sigma, you may recall from previously, stands for sum of. So what we're saying here is the sum of all the forces in the x direction is equal to 0 newtons, and all the sum of the forces in the y direction is equal to 0 newtons. And then if all the forces in the x and all the forces in the y are 0, then obviously the net force is also 0. What that ends up meaning is if an object is in equilibrium, if we are considering friction, that the force of friction is equal to the force being applied. So if we're trying to push a box across the floor, or push a car across the road, or drive a car across the road even, if it's going at a constant speed, you're still applying a force to keep it at constant speed, because now we have friction that would normally slow us down and counteract it, but the two forces are equal and opposite, and so then at least in the same direction, they are equal and opposite. And as I've said already, it does not mean that it is stationary. It simply means that it is not accelerating, not speeding up, not slowing down, not changing direction. A special formula for vertical accelerations only is here. The net force is equal to weight, and recall weight is just m times g, plus the force applied, which is m times a. The masses in both those situations will usually be the same. G, of course, is acceleration due to gravity. It's the acceleration that's being applied to the object that will be odd. And we'll demonstrate this in the elevator sometime soon. So here are two quick examples of force diagrams, force diagrams we use to help us solve problems. I highly recommend a diagram every time you do a problem. But for example, the box on the left-hand side is being pushed to the right, friction is acting to the left, there is a normal support force from whatever surface it's on, and its weight is pushing down, or being pulled down. And those forces are all balanced, and so then this object is in equilibrium and not accelerating. If the forces are not equal, then it's accelerating. Versus the other diagram here, this one shows an airplane in flight and tosses out some of the kind of special terms that we use when we're in the air, or sometimes that get used interchangeably with some of the others. So this one's moving in the opposite direction, but the force applied here is called thrust. The force of friction or air resistance is called drag. Instead of a support force or a normal force up, we call it lift here in flight. And of course, its weight comes from the force of gravity. So just some different ways to label it. Even though we normally do force diagrams, and I highly recommend drawing a sketch, one thing that we do a lot of is free body diagrams. And free body diagrams just help us visualize the vectors. The left one here is a force diagram. The right-hand one is a free body. It's the same diagram without the body or without the object in there. It just makes the calculations a little bit easier. Technically speaking, when you draw these, you should try to draw the vectors to scale. It will help with visualizing, and it will help with estimating answers. I'm not super picky about it, and if you put the box in there, I'm not going to throw a fit. I have never seen the point, to be honest, of totally eliminating the body unless the body is getting in the way of the calculations. Also, I should point out that over here on the pulley, that this object on the pulley does have its own forces acting on it. This free body diagram is only looking at the box and is not looking at the object on the pulley. It's also not looking at the forces on the ramp here, though usually we don't talk about those forces. And we'll do some example calculations of those soon here in class. If you have any questions, bring them with you.